Friends, good evening. How are you? Our today's topic is moving charge and magnetism. This chapter contributes two to three questions in NEET. That is 8 to 12 marks in NEET. In May 3rd exam, they have given three questions from this chapter. Okay, in this chapter, I actually want to revise some concepts first, important concepts, along with some problems, and then we go into problems. In this chapter, let us make this chapter into three parts. First part is magnetic field due to current carrying conductors. Second part is force on moving charge in magnetic field, force on current carrying conductor in magnetic field with force. And third part, instruments, galvanometer, ammeter, voltmeter. Let us divide into three parts. First part, magnetic field due to current carrying conductors. This first part, if you take, you need to focus first on Bird-Savart law. I'm writing BS, Bird-Savart law. Magnetic induction due to a short current carrying element given by Bird-Savart law. What is the magnetic induction because of a short current carrying element? dB equal to mu naught by 4 pi IDL sin theta by R square. I is current, DL is the length of that short element, theta angle. Which angle? Suppose if this is the short element of length dl and current is suppose in upward direction, I'm taking current. At some point here, if you want magnetic induction due to this, if the distance from element to point is r, the angle made by this line joining element and point with current direction, that angle is that. With current direction, this line making how much angle? That is theta. Now this in vector form, if you write dB bar is equal to mu naught by 4 pi I into dl bar cross r bar by r cube. R square. So in vector form, for example, the problem is given like this on Bird-Savart law. An element of length 1 centimeter carrying a current 10 ampere along positive x-axis is at origin. The magnetic induction on y-axis at 50 centimeter distance is dash. An element of length 1 centimeter carrying a current of 10 ampere along positive x-axis is at origin. The magnetic induction on y-axis at 50 centimeter is dash. So this is x-axis, this is y-axis. At origin, a short element of length 1 centimeter is there at origin. This short element is carrying current along positive x-axis in this direction. The point where magnetic induction we need to find is on y-axis. It's a distance from the element R value given there, 50 centimeter. Now, to find the magnetic induction at this point due to this small element, Bart's-Savart law formula, if you apply, dB equal to mu naught by 4 pi IDL sine theta by R square, if you apply, mu naught value 4 pi into 10 power minus 7 by 4 pi, current given as some 10 ampere, so 10, and length of the element dl given as 1 centimeter, 1 centimeter in meters, 10 power minus 2, and sine theta. Sine theta. In the theta is the angle between this radius vector line, this position vector line, and direction of current. Angle made by this position vector line with the direction of current, current is along positive x-axis, is 90 degrees. Sine 91. So here I have to substitute 90 degrees by R. This distance given as 50 centimeter. 50 centimeter means half meter now. Half 1 by 2 meter, 1 by 2 square, 1 by 4. 4 goes up. This, so many Tesla. Like this, you need to apply Bart's-Savart law. Okay? Next, here I'll do. Magnetic induction due to a wire of finite length. Suppose there is a wire of finite length, straight wire of finite length carrying a current I. You want magnetic induction at a point P, and that point is at a perpendicular distance R from the straight wire. Draw this perpendicular line, normal line from wire to point, and then join this point with the two edges of wire. Join this point with the two edges of wire and find angle made by these two edges with this normal line. Say this is some theta 1, theta 2, these angles. Now, the magnetic induction at this point due to wire of finite length, B is equal to mu naught by 4 pi into I by R into sine theta 1 plus sine theta 2. This is magnetic induction due to wire of finite length. For example, in a problem, it is given there is a straight wire of length 8 meter carrying a current of 4 ampere, and there is a point here on the perpendicular bisector line. This is perpendicular bisector line. On that there is a point at a distance 3 centimeter, or sorry, this is meter given, this also I'll give meter. At a distance 3 meter, Find magnetic induction at that point is asked. Then join this point with the two edges of wire. This total length of wire is 8 meter. This is midpoint now, so this will be 4 meter. This is 4 meter. Then this hypotenuse length will be 5 meter now, using Pythagoras formula in this triangle. 5 we will get now. This hypotenuse length 5 we will get now. Then this theta 1, theta 2, these two angles you need now. Now substitute here. Mu naught 4 pi into 10 to the power of minus 7 by 4 pi. Current given as 4 ampere by this perpendicular distance of the point from wire is 3 meter given, 3, and sine theta 1. Sine theta 1, 4 by 5, now opposite by hypotenuse 4 by 5. Sine theta 2, 4 by 5. 8 by 5, you'll get 4 by 5 plus 4 by 5. Simplifying this, you will get magnetic induction at this point, so many Tesla or Weber per meter square, unit of magnetic induction. Tesla or Weber per meter square. CGS unit of magnetic induction is Gauss. 1 Gauss 10 power minus 4 Tesla. Remember units also. This is how to find magnetic induction due to a wire of finite length. For example, for a wire of finite length, the point is somewhere here. You want to find magnetic induction at this point. Then what to do? Extend this edge like this and draw the normal line up to wire, perpendicular line up to wire, and join this point with the two edges of wire. Join. This is angle made by one edge from this perpendicular line, theta 1. This is angle made by other edge from this perpendicular line. Here, both the angles are one side of normal. In previous, one angle is this lower side, other is other side now. Here, both the angles are on same side. In this case, magnetic induction mu naught by 4 pi I by r sine theta 1 minus sine theta 2. Minus will be there. Earlier here sine theta 1 plus sine theta 2 is there. Now sine theta 1 minus sine theta 2 will be there. This difference, if both the angles are on same side of normal, this you need to apply for a wire of finite length. Okay? Now wire of infinite length, just I'm revising these points, important now. Wire of infinite length, this edge is at infinite length, this edge is also at infinite distance. There is a point P here. Then this edge, if you join, they're almost 90 degrees. Now each angle, sine 90 plus sine 90, 1 plus 1, 2 you'll get. Magnetic induction mu naught by 4 pi I by r into sine 90 plus sine 90, 2, 1, 2 cancel here. You will get mu naught by 2 pi into I by r. This is magnetic induction because of infinite wire. Semi-infinite wire is there. Semi-infinite wire means the wire is of infinite length, current carrying wire is of infinite length, but the given point P where magnetic induction is needed, that point is exactly opposite to one edge of the wire, semi-infinite wire. Here what will happen? One angle will be 0. One angle will be 90. That's why sine 0 plus sine 90. Sine 0, 0. Sine 90, 1. 0 plus 1, 1. So what you will get? Magnetic induction here, mu naught by 4 pi into I by R you will get. Here 1 plus 1, 2 cancel, 2 pi into I by R. There 4 pi into I by R. This is magnetic induction due to straight wire of infinite length, semi-infinite length. Next to curved wires. Suppose the wire is in the form of arc of a circle, current carrying wire, which makes an angle theta at the center of circle. Then the magnetic induction at this center, here at this center, magnetic induction due to this current carrying arc, mu naught by 4 pi into I by R into theta, where theta is this angle. Suppose if it is semicircle makes how much angle? Pi radian. Here pi, one pi will cancel. You will get B formula mu naught by 4 pi into I by R. Suppose it is a circular loop, then the angle will be 2 pi. No? So here 2 pi, 2 times cancel. So you'll get B equal to mu naught by 2 into I by R. Pi will not be there. Pi will cancel now here. Mu naught by 4 into I by R. There mu naught by 2 into I by R. Pi cancel now. In the curved wires formula, pi will not be there in the denominator. Pi will get cancelled after substituting theta. This is magnetic induction due to curved wire. If it is a circular coil of n turns, Ni, mu naught Ni by 2R, you will get Ni by 2R. These are different magnetic inductions in different cases. Solenoid, you remember na solenoid, magnetic induction inside solenoid. Inside solenoid, magnetic induction B is mu naught Ni, where N is number of turns per unit length. And magnetic induction at one edge mu naught Ni by 2 you'll get. At one edge mu naught Ni by 2. Revise these all. Make this chapter into 3 parts. Magnetic inductions due to current carrying wires. First part. Second is force. Force on moving charge, force on current carrying conductor in magnetic field, that force related. Third, instruments, galvanometer, ammeter, voltmeter. 3 parts. Part wise, each one thoroughly revise. Very easy to score, straightforward, formula based questions. Direction, in which direction that force will act on charged particle. Fleming's left-hand rule you have to apply now. That rule application questions and that Ampere's right-hand thumb rule to know in which direction that magnetic induction will act, to know that. For example, this is a straight wire carrying current I. One point I'm giving on right side of this wire, let us say east, this is west. My back side, this camera side, south, this direction, what I'm facing is north. Like this, now I have to take. Right hand side east, west. What I'm facing is north. My back side is south. Now here current is upward, vertically upward. At this point, what is the direction of magnetic induction? If it is asked, that Ampere's right hand thumb rule. You need to apply now. Keep this finger, thumb in the direction of current and hold this wire in your right hand, keeping thumb in the direction of current, and these remaining four fingers, when they are curling around wire, when they are curling like this, near this point, how these fingers are going, which side they are going, you see, they are going inside towards north. So here, magnetic induction due to the wire here will act towards north. Suppose the point is given here. Here, what is the direction of magnetic induction? Hold the wire with in right hand, thumb upward, current upward, not thumb upward, and try to hold this like this. Now these four fingers, remaining four fingers curling around this, near this point, they are coming out like this. Out means this side, back side, south. So here magnetic field due to this wire will act towards south, here towards north. Like this, applying these rules, finding the direction of magnetic field and that force direction, applying Fleming-Sand rule, these direction-based questions also they are asking. And when a circular coil carrying current, suppose this circular coil carrying current, from this side, if I look into this surface is appearing to carry current clockwise. From this side into same coil, if I look from opposite side, then it appears to be current in anti-clockwise. See, if I am rotating this pen like this, for me this is clockwise, for you it is anti-clockwise. Same thing, from this side appears clockwise, from opposite side appears as anti-clockwise. No? Like that, there is a coil here. It is carrying current. If I look into this from this side, it's carrying current, appears to be carrying current clockwise. Same coil from back side, if I see, appears to be carrying current in anti-clockwise. Whichever phase appears to carry current clockwise, that will act as south. And the back side, rarer side, will act as north. Remember that. Then the magnetic field acts along this axis now. Here, if I keep a unit north pole, due to this circular coil, this front side is acting as south pole. No? It will attract this. Means the force on this unit north pole will act inward. If I keep unit north pole here, it is repelled by this back side of coil is acting like north, rarer side. It will repel this. So here also B will act this side only. No? So inward, along axis, inward, the field will act. Like this, these directions also important. Very important. Next, motion of charge in magnetic field. When a charged particle moves through a magnetic field, the magnetic force experienced by that moving charge is given by BQV sin theta. This in vector form, if you write, it is Q into V bar cross B bar. Q into V bar cross B bar. This is force. The force is maximum when the charged particle, if this is magnetic field direction, charged particle moving perpendicular to field, then this force is maximum, and that maximum force is BQV. And this force always acts perpendicular to the plane. Magnetic force, remember, This is very important. On a moving charge in magnetic field, magnetic force will always act perpendicular to the plane in which the moving charge and field are present. Means it acts perpendicular to the direction of motion of charge. Whenever a force acts perpendicular to velocity vector, in whichever direction particle moving perpendicular to that, if any force acts, that force can change only direction but not the magnitude of velocity. That's why in a magnetic field, magnitude of velocity of the charge constant, direction only changes in this case, direction. Magnetic, that velocity of the moving charge remains constant magnitude. Means momentum, linear momentum also, magnitude constant. Direction of movement, linear momentum changes. Kinetic energy, scalar, it will not have direction, constant. So kinetic energy, magnitude constant, it doesn't have direction. So kinetic energy constant, you can write. Velocity and linear momentum, they are not constant. So they are constant only in magnitude, direction changing. A vector is said to be constant only when it is constant both in magnitude and direction. Here, direction changing, then how can you say velocity constant? Velocity variable, variable in direction. Magnitude constant, direction variable. Linear momentum also, they are changing. And work done by magnetic force on moving charge 0, because this force acts perpendicular. So work done 0, no change in kinetic energy. Very important points, these points. Okay, in this case, when the charge is moving perpendicularly like this force BQV acts like centripetal force. BQV will act like mv square by r. That means it will deflect on a circle. That circle radius is mv by bq. Radius. mv momentum can be written as root 2m into kinetic energy, from kinetic energy momentum relation by bq. Very important formula. And the time period, time taken to complete one rotation on that circle, 2 pi into m by bq, time period proportion to mass, inversely proportional to charge. Time period is independent of velocity of the moving charge. Remember, time period is independent of velocity. Radius depends of circle depends on velocity. Time period independent. In this one, important question is there. One proton, one deuterium nucleus, one alpha particle helium nucleus, these three, proton, deuteron, alpha particle, these three enter a magnetic field at right angles. Enter at right angles, they'll give. And they ask, find the ratio of radii of the circles on which they deflect. Giving condition, they'll ask, find the ratio of radii of their circular paths. Giving condition, one condition, if they enter into field, with same velocity, they give one condition. If they enter into the field with same velocity, what is the ratio of the radii of their circular paths in the field? Then velocity is same, B same, in same field they entered. So you should take R proportional to M by Q. R proportional to m by q. Radius of proton path, radius of deuterium path, radius of alpha particle path. These three radii, if I write, proton mass by proton charge is to deuterium mass by deuterium charge, alpha particle mass by alpha particle charge. I have to substitute. Now you take proton mass and proton charge 1 you take. Ratio only, na? Proton mass 1, charge 1 you take. Deuterium, next particle, second one is deuterium. No? Its mass is 2 times to the mass of proton. But charge is same as proton charge. Alpha particle mass 4 times more than proton. But charge is 2 times more. Charge, 2 protons are there in alpha particle. So Q alpha 2 times 2 proton charge. Ratio you'll get. Very important. Or another condition they'll do. If they enter into field, with same momentum, they will give. Same momentum P. Then MV same. MV same, B same. In this R equal to MV by BQ, what is MV? Momentum. It is same, B same. So R inversely proportional to Q. You have to apply and find the ratio in a similar way. Third, they enter into field with same kinetic energy. These three particles, find the ratio. Same kinetic energy, this root 2m Ke by Bq you take. K is same, B same. Then R proportional to root m by Q. R proportional to root m by Q. Apply this, find the ratio. This is very important models. Next, force on current carrying conductor when kept in magnetic field BIL sin theta. In vector form, it is I into L cross B. I into L cross B. Suppose a wire of length L carrying a current I along carrying a current I along positive x-axis is in a field of B bar equal to 2I cap plus 3J cap minus 4K cap Tesla. Find the force acting on this wire, they're asking. This vector form you have to apply. How to apply this vector form? I given. I. L bar. What is L bar? The length of the wire is taken as vector here. Then what is the direction of that length vector? Length vector direction is current direction only taken as L bar direction. Current direction here is along positive x-axis given. L bar direction also is along positive x-axis. So L magnitude L given. Length magnitude L given. So L you write. Vector form you have to express no? L into I cap, you write it. L into I cap cross B bar. B bar given 2I cap plus 3j cap minus 4k cap given. Find now. Find I into I cross I 0 now. I cross I 0. So first to 0. L also I'm writing outside this L also. I cross I 0. I cross J K na. So 3 you'll get, K you'll get. Then I cross K. I cross K minus J. And here already one minus is there here. And I cross K is minus J. Another minus coming means plus you'll get. 4J you'll get. This is the force. And this 3k cap plus 4j cap vector magnitude is pi na, root 3 square plus 4 square. So if you want the magnitude of this force, this magnitude is 5 root 3 square plus 4 square, 5IL. 5IL is answer. That is force on moving current carrying conductor in a magnetic field. Next, there is one cyclotron is there now. Cyclotron. The cyclotron is a particle accelerator. The cyclotron cannot accelerate electrons, lighter particles whose mass is very less. It cannot accelerate. It cannot accelerate cyclotron. Lighter particles, it cannot accelerate. Reason is, according to Einstein's relativistic theory, whenever a particle is in motion with high velocity comparable to velocity of light, its mass changes, increases. That relativistic mass m is m naught by root 1 minus v square by c square, where m naught is rest mass of that particle. Now, if this velocity, this v is velocity of particle, c light velocity. If this v is very less when compared with c, negligible. Na? So this v square by c square negligible, m is m naught. But when v is very high, comparable to velocity of light, then mass m will be greater than m naught. Now, electron, suppose if you take, it is lighter particle, no? Very light electron. This electron, as the mass of electron is very light, when you are accelerating that in an electric field, acceleration EQ by m, this m is very less. So acceleration is very high. So in a short time, quickly, electron will reach to very high speeds comparable to light speed. Very close to light speed, it will gain. That much speed electron will gain. Then its mass will increase. As mass increases, what will happen, in the cyclotron, time period of this particle revolving in the circle due to magnetic field is 2 pi into m by bq now. In the cyclotron, two D's are there, no? D's, remember that? You have learned this? D's. Array. Like this D shape. And between them, this electron charged particle will accelerate like this. In one half rotation, it will be moving from D1 to D2 now. Suppose that is a partially charged particle. Let us take partially charged particle. When it is moving towards D2, D2 should be negative, D1 should be positive. Then only that partially charged particle will be accelerated. Then after half rotation, when it is coming from D2 to D1, this negative positive, that electric field must be reversed. Then again it will be accelerated. If it is not done, what will happen? After half rotation, when the charge is moving from D2 to D1, if this is still positive, this will repel that a partially charged particle coming like this and retards it instead of accelerating. That's why they should interchange. That electric field should flip off. It should change at regular time intervals. The time period at which the electric field gets reversed also must be equal to this. Equal to this. So they will adjust that. The time period of electric field equal to this, they will adjust. But here what is happening? If the electron is reaching high speed equal to comparable to velocity of light, its mass increasing. Time period will increase. Time period of electron. As time period increases, electron moving slow here, electric field is changing fast, electron has become slow, and this mismatch, the time periods of electric field, time period of revolution of particle, mismatch. The time period of electric field, time period of revolution of particle must be
अच्छा
equal
कुछ
there.
भी याद दिला तो
That is
वापस आके
resonance condition
वो कहीं को लेके
that it
जाती थी,
gets missing.
ये कहीं को लेके जाती
That's
थी.
why you cannot accelerate lighter particles. Electron lighter, na, so you cannot accelerate. Next to that galvanometer, BINA, the torque acting on the coil in galvanometer, must be equal to C theta, restoring torque in that phosphor bronze twisted wire. This is relation I proportional to theta in galvanometer. Sensitivity of galvanometer. What is sensitivity of galvanometer? Deflection per unit current theta by I. That theta by I is BNA by C. You can increase sensitivity by decreasing C, by decreasing this restoring torque per unit twist, increasing number of turns. This is about galvanometer. Now, this galvanometer can be converted into ammeter and voltmeter. You know that ammeter, by connecting shunt to galvanometer, you can convert galvanometer into ammeter. Then if the total current entering I, a part of that will flow through galvanometer coil, remaining will flow through shunt. This current through galvanometer formula I into S by G plus S. Cross multiplying this shunt resistance IGG by I minus IJ, you'll get ammeter. Ammeter should have low resistance. Ammeter, ideal ammeter resistance is 0. Ammeter must be connected in series only in the electric circuits. It is converted into galvanometer converted into ammeter by connecting low resistance in parallel, shunt. But this ammeter in electric circuits to measure current must be connected in series only. This is ammeter. Let us see one example in ammeter. Ammeter. See this? See this? The deflection in galvanometer reduces to 1 by 5 when shunted with 4 ohm. When it is further shunted with another 4 ohm, then the deflection reduces to dash. Nice. See this problem, how to solve ammeter problem, shunt. See, first you have only galvanometer and you are sending some current I. This total I will flow in galvanometer coil only. And due to that current, it is showing a deflection theta. Now you have connected a 4 ohm shunt to this galvanometer of resistance G. You have connected a 4 ohm shunt. Then again same I current you are sending. Then total I will not flow in this. A part of I will flow, Ig. Means less current flowing no, in galvanometer now than earlier. So deflection decreases because theta proportional to I no, in this. And what is telling deflection decreased to 1/5, 1/5. Means deflection becoming theta by phi. Why? Why the deflection becoming theta phi? Theta by phi because Ig becomes I by phi. Earlier I current flowing, now Ig flowing. No? This Ig is I by phi. That's why. Now apply that formula. Ig equal to I into S by G plus S. Ig I by 5 given, I into shunt 4 given, G plus 4, I cancel, G plus 4 equal to 20. That indicates galvanometer resistance 20 minus 4, 16 ohm. This you'll get. Now come to next sentence. When it is further shunted with another 4 ohm, further shunted with another 4 ohm. See, here I am drawing. Galvanometer already has 4 ohm shunt. It is further shunted means another 4 ohm connected in parallel to already that 4 which is existing. 4, 4, 2 are in parallel there. If 2, 4, 4 are in parallel, what is the effective shunt to 2 ohm? So this galvanometer effectively has how much is shunt now? 2 ohm. 2 ohm. Now the deflection reduces to how much is asking. Means Ig is how much of I you find now. Again Ig formula you apply. I into S by G plus S you apply. Ig equal to I into the new shunt is 2 na, effective shunt is 2 na. 2 by G plus S, 16 plus 2, 18, 2 9 times cancel. You are getting Ig equal to I by 9. That means the deflection reduces to 1 by 9. 1 by 9, that is answer. Like this ammeter conversion problems. Just one problem model I have discussed to just to remind you all, know all this, just to remind you. Okay? Like this voltmeter, you know, it is galvanometer converted into voltmeter by connecting a high resistance in series. Voltmeter should have high resistance. Ideal voltmeter should have infinite resistance. All this. Now let us come to some other additional problems now. Overall, some revision of chapter briefly I did. Now see this. A charged particle moves with some initial velocity along the direction of an external magnetic field. There is a magnetic field of magnetic induction B. A charged particle is moving in the same direction along the direction of magnetic field. That means this charged particle doesn't experience any magnetic force, zero, because it is moving parallel to field. BQV sine theta, theta 0, so force 0. So it continues to go on this straight line like this only, because force 0. That is given. Now what he applied? If we apply uniform electric field perpendicular to magnetic field. Now this is magnetic field, no? Perpendicular to this, he applied one electric field. Then what will happen is asking. If you apply electric field like this charged particle already moving along magnetic field with a velocity v. If you apply perpendicularly electric field in this perpendicular direction, electric force EQ will act. Due to this, it will gain velocity along this y-axis. Means this particle will have two velocities now. One velocity along magnetic field, one velocity perpendicular to magnetic field it will have. Due to velocity along perpendicular to magnetic field, it will experience, that magnetic force BQV and revolve on a circle. Due to this velocity perpendicular to magnetic field, it will experience magnetic force and it will act as centripetal, it will revolve on a circle. And due to this velocity, which already it has along magnetic field, it will have linear motion along this straight line like this. So it has to move straight like this, it has to make circular motion, means it will move on helix. So answer is helix. Understood? I'm going into next problem. A long straight rod of diameter 4 mm. Oh, this is not thin wire, cylindrical, long cylindrical rod of diameter 4 mm means radius 2 mm. Carries a current I. The current is uniformly distributed across its cross section. It is a solid cylindrical conductor. Inside current is there, is not a hollow is not hollow cylindrical conductor. Current is distributed uniformly throughout the cross section. The ratio of the magnetic field at a distance 1 mm and 4 mm from the axis. This is the axis, no? Middle line. 1 mm means inside, 4 mm means the point is outside. Very good question. So take one long cylindrical conductor. You take one point inside at a distance small r. There, small r less than capital R. Capital R as radius of wire I am taking. There, magnetic induction formula mu naught by 2 pi into I into small r by capital R square. This is magnetic induction inside the cylindrical conductor. Okay, let us find this. Mu naught by 2 pi, mu naught by 2 pi, mu naught 4 pi into 10 power minus 7 by 2 pi. Current I. What is small r given? Small r, small r, 1 millimeter. Okay. Millimeter. I'll keep like that. Just we are finding ratio only, 1. What is this? Oh, okay. By r square, capital R square. What is capital R? Radius of the wire. That is 4 mm. Diameter. Radius 2 mm. Na? 2 square. Radius 2 here. Remember, 2 square, 4. Just units I'm not converting. Just ratio. Na? Now, at a point outside this, when small r greater than capital R, at a point outside, what is magnetic induction due to this? Mu naught by 2 pi into I by R. Okay, this 4 pi into 10 power minus 7 by 2 pi into current to I by, that point is at how much distance from the center? That small r how much given? 4 millimeter given. 4. Arre, kya is, I'm getting same. Inside I by 4, outside also I by 4, ratio 1 is to 1. 1 is to 1. Fourth option. For this BR graph also, remember earlier, I think 2022-23, they asked this graph, BR graph. inside the conductor B directly proportional to R, straight line you will get up to capital R distance. Outside B inversely proportional to R, B inversely proportional to R outside. This rectangular hyperbola you will get. क्या बोला? Rectangular hyperbola. If it is hollow cylinder, if it is inside field zero, inside field zero, if it is hollow. So when smaller less than capital R, field zero na, on x-axis you will get straight line. No? Then like this you will get. Graph hollow. This is solid cylindrical conductor. Okay, I'm moving into next problem. A galvanometer coil has a resistance of 80 ohm and current for full scale deflection. Galvanometer resistance 80 ohm and galvanometer needs how much current? 10 milliampere for full scale deflection. Means this is the maximum current that it can measure. A resistance of 920 ohm is connected in series with the galvanometer. To make it a voltmeter, very good. Correct only, no? High resistance in series to connect, no? To make it into voltmeter. If the least count of the voltmeter is 0.2 volt, then the number of divisions on the scale mean least count means sensitivity. 0.2 volt per division. Per every division reads 0.2 volt in this voltmeter, he is telling. Total how many divisions are there? Means you find what is the maximum voltage that you can measure with that voltmeter. What is voltmeter formula? V equal to I into G plus R. Find it. What is I? 10 milliampere. 10 milliampere means 10 power minus 2 ampere. 10 into 10 power minus 3 into G 920 plus, sorry, G 80 R 920. Add them 1000 you will get. Means what you are getting? 10. V10 you are getting. Every division will measure 0.2 volt. Total voltage measure 10. So total how many divisions are there? 10 by 0.2, 100 by 2, 50 divisions must be there. 50. Moving into next. Which of the following graphs correctly represents the variation of magnetic field with distance from long, straight, thin wire? In the magnetic field of this B is mu naught by 2 pi into I by R, B inversely proportional to R due to a straight thin wire. Means this rectangular hyperbola, fourth option, D. A beam of electrons passes undeflected through mutually perpendicular and magnetic field. There is a magnetic field, electric field, both are there. And electron beam passing undeflected, without deflection, is going straight. That indicates that the magnetic force BQV, electrical force EQ are equal and opposite, cancelling each other. That's why it is going straight. That is this. Now, if the electric field is switched off, what will happen? If you switch off this electric field. What will happen? Only magnetic field is there, only magnetic force is there. And because of that magnetic force which acts perpendicularly to the motion of this charged particle, it has to move on circle. So it will move on circular orbit. Next, so and charge so and so is moving at a speed 10 kilometer per second in a circular path of radius 2 point inside a solenoid. The solenoid has 25 tons per centimeter and its magnetic field is perpendicular to the particle path. The current in solenoid means a charged particle is moving on a circle in a magnetic field. Whose magnetic field? Solenoid magnetic field it is. And the radius of that circle given. What is radius of circle formula? mv by bq. This B is magnetic induction due to solenoid there. Means this B is mu naught Ni. B is mu naught Ni. So mv by mu naught Ni. This N is number of turns per unit length into Q. B mu naught Ni I am writing. Now he's asking current now. I. Cross multiply like this. mv by mu naught NQR, I think. Now substitute mass given, mass of the particle 2.2 something given. 2.2 into 10 power minus 30 kg SI unit given. 30 mass V velocity 10 kilometer per second. You have to substitute in meter per second. 10 into 10 power 3. 10 into 10 power 3, 4 MV. Mu naught value 4 pi into 10 to the power of minus 7. N number of turns on solenoid per unit length 25 per centimeter he gave. 25 turns per centimeter he gave. This you have to convert into meter. 1 centimeter is 10 power minus 2 meter. This will go up. 10 power minus 2 becomes 10 square. 2500. 2500 turns per meter N value. Q given somewhere QQ. 1.6 into 10 power minus 19. That I am writing 16 into 10 power minus 20. This 1.6 into 10 power minus 19, I wrote 16 into 10 power minus 20. Radius 2 centimeter he gave. 2 centimeter is 2.8 into 10 power minus 2 meter. This also I'll write like this. 28 into 10 power minus 3. Like this if you write, easy calculation. The decimals confuse you. 28 into 10 power minus 3. Simplify this, you'll get the current in that. Okay? Okay, students, all the best. Revise these areas. Magnetic induction due to current carrying conductors, one part. Force experienced by moving charge and current carrying conductors, force between two parallel conductors. If they carry current in same direction, they attract each other. If they carry current in opposite direction, they repel. That is there, that. And then these instruments, galvanometer, ammeter, voltmeter. Revise them. Very easy this chapter, straightforward questions, direction-based questions, formula-based questions they are asking. Right, thank you all. All the best.